Hello and welcome to today's webinar. My name is Tyler Reid. I'm the Manufacturing Application Manager here at GoEngineer. Today's webinar is titled 3D Printed Car Parts. Today we're going to be covering car parts that I did basically as a selfish project here. I'm going to be covering the parts as they're designed through creation, through 3D printing. We're going to be talking about some of the pitfalls that I had to hurdle, some of the pitfalls that I kind of fell into, and some of the things that I did right as well. I chose this topic because I think it's approachable to a lot of people, especially guys who work on their own cars. And this is something that I did within the span of a few days. And so I feel like it's very approachable to anybody that is used to working with tools, used to working with the printers, used to working with CAD, and just has a mindset of tinkering, which most people who are into 3D printing have. So 3D printed car parts, cars in particular pose a few different challenges to us. For one, we're normally working with an existing model, existing car that has limited space. So most of the parts that I'm going to be talking about today are parts that I put in the engine bay of the car. Within the engine bay, we have all sorts of vacuum hoses, wiring harnesses, random plastic parts that you have no idea what they do. You have to work around them. So limited space was a key factor here. Difficult fitment. This is another one that came up quite a bit in my journey on the car part webinar here, is getting the fitment right on the parts. Again, we don't normally have CAD models of, say, the chassis of the car or the head of the car, the valve cover, the block, but we're trying to fit up parts to those pieces. And so we have to use some tricks. We can use photographs, we can use scanners, we can use our calipers, but that's a difficult portion, especially when you combine the limited space factor, where if you're trying to fit parts within a limited space, you might only be able to access it from one direction. So your parts have to be able to conform in that. Those two steps together cause a lot of headache in the prototyping phase of our design, because even if we get all of our mounting spots in the correct spot, the size is correct, we might have an assembly issue. And unless we have a physical prototype, that assembly issue, the actual physical process of installing it into the car, can be very difficult to anticipate. I didn't run into that a lot personally because the car that I was working on is more of a show car / track car, so a lot of the engine bay has been cleared out, but there was some of that. Also, if we're talking about functional parts, which we are going to be covering today, we have to deal with heat and exposure to the elements, exposure to vibration, chemicals, and whatnot. And so those are two issues that come up. They may come up in terms of functional prototypes or end-use parts. So at least one of the parts that I'm going to talk about today, I plan on keeping in the car until it fails, which may be a long time. And some of the other parts, it's more for just a prototype where I can take that info that I gained from that prototype and go into some other sort of manufacturing, whether it be sheet metal or some sort of handcrafted fiberglass, carbon fiber part, something like that here. Before we go on, I'm going to be trying to cover all of this content that I have within about 30 minutes. So it's going to be a little bit fast paced. If you have questions, I cannot hear you. So go ahead and speak into or type into the questions box within the GoToMeeting control panel there. I may take questions throughout, or I may leave them towards the end. So go ahead and just type them when you have them. Also, this is being recorded and will be available on our YouTube page if you want to view this later. All right, so the two types of printed parts we're really going to be focusing on today, functional prototypes. So prototypes are created to test form, fit, and assembly. Make sure they're the right size, make sure if they're enclosures, you can fit everything into them, and make sure you can assemble them, but also function. Can I, say, expose this to heat, expose it to vibration? If I have a particular part that needs to screw on to another part, will it screw on? So these are going to be functional prototypes. And then also end-use parts. parts that intend to stay on the car or intend to stay wherever they are in printed form. Great thing about end-use parts in automotive design and aftermarket automotive design is that you can create custom, unique designs that you wouldn't normally create using conventional methods. Personally, with GoEngineer, we've worked with quite a few aftermarket automotive companies to create custom designs, and some of them are one-off designs that you might see on, say, Counting Cars or Bitchin' Rides. TV shows, they're all about creating over-the-top things that are all custom. We've worked with them to create 3D printed parts. Looking at them, though, you would never know that they're 3D printed because a lot of end-use parts are post-processed. They're sanded, they're painted, they're coated, they're hydro-dipped, all sorts of things that we can do to these plastic parts. To go along with the custom unique features, a lot of times we're implementing extra features. So we come in with an initial idea, we need a part to achieve some sort of task, and because we're working with the 3D printing, a lot of times you can add extra features at little to no cost. I'll talk about a couple examples of where I did that in my process, and this can be a great thing because you end up with smarter parts, more intelligently designed parts, but it can also be a bad thing too because you tend to get feature creep, meaning you design a part to do one thing and you tell yourself, you know what, if I spend a half hour more, I can add this feature. And you do that 5-6 times and all of a sudden you've got a Swiss Army part that you really didn't want. So feature creep is something to be aware of. And then lastly here, all of these parts can be easily iterated for improvements or fitment issues. So fitment issues is a huge one because of the two reasons we talked about earlier. You're not dealing with a CAD system, you're dealing with, say, templates and photographs and whatnot, but also easily iterated for improvements. So a lot of times you're prototyping a part, you're testing it, you're gaining some info from it, and you realize that even though this works, there's some improvements that I can make to it. And because the prototyping time and cost is so low, we can implement those improvements really easily. So the car, this is a before picture of the car. This is my personal car. It's a Volkswagen GTI. It's got the 1.8 T motor in it. This is a picture from about a year ago. You can see it was in pretty rough shape. The bay is, I would say it's mostly stock. There's some non-stock things in here. The turbo, all the turbo piping, catch can over on the right-hand side. You got a secondary fuel pump over on the left-hand side. But the engine bay is a mess, all right? If we were working on this engine as is, it would be very difficult because, again, it's very cramped. There's not a lot of room for things to breathe. There's not a lot of room for things to fit in. So I've been working a lot on this car over the past year, and I have it looking something like this. So this is the same car with a lot of work put into it. A lot of the parts are different, but a lot of them are the same. I did a lot of the powder coating myself in my garage, and the same functional car. It's just got a lot of extra things removed. Battery's been relocated to the rear, which is causing problems, which is something I addressed here in this project. So this is what we're working with. The parts that I created for this little presentation, again, parts that I had on my mind that I wanted to print for a long time, I just never got around to it. These are the order we're going to talk about them. I've ordered them in how I felt in difficulty. So the gauge bezel I felt like was the simplest project to take on, and then the battery charging box was probably the most involved. So we're going to step through these. We're going to be in the PowerPoint mostly, but I'm going to jump into SolidWorks a little bit. I'm also going to jump into the Stratasys Insight software a little bit to talk about some things that I did on these parts. So before I talk about each part, I have a slide that looks like this. It's basically overview of the project, and then we're going to go into photos. All right, so the problem I was facing with this gauge bezel is the bezel that I had and the gauge that I had, it sits on top of the steering column, and the bezel, the front part of that gauge, was too tall. So it actually interfered with the steering wheel, meaning if I tried to steer it, it hit the bezel. So what I needed, the solution to that problem, was just a shorter bezel. All right. And the manufacturer of that particular gauge didn't provide a shorter bezel. So it's up to me to either create one or figure out a different way to mount it. And this was just the easiest solution here. Added features, there was nothing really to add to this. I was just going to basically copy the design, copy the existing design, measuring using calipers, and then adjust it so it was a little bit shorter, and print it out. I printed this on our Connex 350 in Salt Lake City, and the material I used was Vero Clear. So the material in this case was not too important. I only used Vero Clear because it's what was loaded on the machine. But using the PolyJet technology, the Connex machine, could have been an Object Pro or any of the PolyJet machines. The big thing there is that I needed some printed threads, and they needed to be fine enough that I could screw it on. And this ended up being about a 16 pitch thread. So pretty fine threads. That was the most important. I didn't want to use FDM. So the positives, again, this is a little bit of an overview before we jump into the pictures here. The positives of this project, it worked, all right? The shorter bezel cleared the steering wheel, no problem. And it also fit well, all right? So I was able to screw it on to the gauge, no problem. I'm sure my threads weren't perfect, but since this is a little bit softer material, I was able to screw it on, no problem. My concerns, I'm concerned about the durability. So the downside of using the PolyJet part is that they're not as durable as the FDM thermoplastics. Ideally, I would be using an ABS or a nylon or a black Ultem for its heat resistance and even ASA now for its UV resistance. But I use the PolyJet for the threads, which means I'm probably going to be having some issues come summertime if this stuff is in the heat, and over time, UV resistance. I've left it uncoated. I could paint it and give it some more UV resistance. So potential improvements: a different material choice, sticking with the PolyJet technology, but doing a digital ABS material would be a lot more solid. Or even printing out like a little short run injection mold of this and doing a benchtop injection mold, a one-off thing. So you've got two images here. These are the cross sections of the file. You can see I've shortened it, 1/8 of an inch or so. This is an image of the bezel as it just finished printing on that Connex 350. We've got the clear material and some interior support material. Held up to the light, you can see the support material a little bit better. On the PolyJet machine and the Connex machine, you do have some choices as to how dense your support material is. I chose the least dense support material here because I knew I was going to have to remove it from the threads. Now, it's very soft. The support material on the PolyJet side is kind of waxy, and so I was able to easily remove this anyway using the water jet. The water jet, we call it a water jet. It's really an electric pressure washer within an enclosed structure. I wish I had a picture of that, but we just shoot it with some water. It's a physical removal process, and it comes out looking something like this. So here's an image, the printed part on the left and the injection molded OEM part on the right. So it's almost an exact copy. I did my best with the calipers. I just made some basic measurements. I did the thread using a swept solid. All right, a lot of times people do threads with swept cuts. I just did a swept solid, not a big deal. So this was very simple, very approachable. The design and measuring probably took me 40 minutes. The printing on this took about an hour and a half. The support removal probably took 15 minutes. All right, so overall, this is a morning project. And then here's a shot of the gauge behind the steering wheel. You can see it clears there on the left-hand side. We have a little bit of a gap here. Whereas the black gauge hit the steering wheel, so either the gauge was going to move or was going to break when you turned. So that's problem number one. Part number two. I called it a firewall feed-through. I don't know if this was the best name for it. This is really, it's not a bulkhead because a bulkhead has terminations. This is something that's going to let the wires feed through the firewall from the rain tray to the engine bay, okay? The problem was it was just an open passage. It looked ugly. The wires could have rubbed up against the firewall edges and had some irritation there or shorted out there. So I needed something to kind of contain it. Again, no real added features here. The measurements I took I used a tape template, and I'm going to talk a little bit about that in the photos here, but I basically used masking tape to create a template on the car and then use the calipers on the masking tape. This was printed on the U-print using ABS material at 13 thousandths slice height, which is the most coarse slice height that we have available. The reason I did it most coarse is because I was under kind of a time crunch. So just to admit to everybody here, today's Wednesday. I left town yesterday, so I had to have all of this completed by Monday night. I started designing these parts on Thursday, so I spent Thursday and Friday designing the parts, a little bit of Saturday morning designing the parts. Saturday and Sunday I spent printing and finishing the parts, and Monday I spent installing them. So overall, this is about a 4-day process for 5 unique parts, which is actually pretty quick, especially for what we've done here. But I think I could have done a little bit better job if I had given myself more time, but this is the reality of it, right? We're trying to pump out parts as quick as we can. So anyway, I used the most coarse printing height because I needed it to print quick. Positives on this, it was a simple aesthetic solution. It worked. The concerns, it was a tight fit. I actually had to use a hammer to press it into place or tap it into place. These parts, because they were so coarsely printed, they did need additional post-processing. And the shape wasn't 100% correct. So my tape template wasn't done as well as I could have done. And so it's going to require either I reprint the part or I adjust it with a Dremel. Some potential improvements. I could have made the part thinner. I'll talk a little bit about that in a more accurate shape. Just to show you guys real quick how this part was designed. It looks something like this inside SolidWorks. If we open this part, it's a 2-piece part, but I created them together. All right, so I created this shape here as one piece, and then I used a surface that looks something like this to make the cut. And at this point, I created a second configuration within SolidWorks, because when I do a surface cut, it cuts away half of the model, and that model is not recoverable. So I actually did 2 surface cuts, one in each configuration. One surface cut cuts away the bottom, one surface cut cuts away the top. And then in my assembly, these are actually 2 of the same part. I just have different configurations showing. All right, so that's kind of what it looked like on the SolidWorks side. So here's the problem visually. We're looking into the rain tray. This is the top right corner of the engine bay. And the problem area is kind of here. Up in the top, those wires passing through the firewall. I wanted something that was going to hold those wires and look a little bit better. So this is a very high-tech visualization of what my masking tape template looked like. All I did was I spread the masking tape from one side to the other, just bridge that gap. I did it on both the front and the back, so they stuck together. I layered up a few different layers so that I could get some thickness on that, and then I just ran an X-Acto knife down along the walls of the firewall and cut it to shape. And now I had sort of a template that I could use to create my SolidWorks file, and that's what I started out with. I did just a basic square like this, or a basic rectangle, which actually didn't quite end up being correct. So this was the finished printed part. Again, this is on a U-print on 13 thousandths. It's very coarse. I wasn't too happy with this. I didn't want to put this in the car as is, so I did some post-processing on it. I had never done solvent smoothing. A lot of people call it vapor polishing, vapor smoothing. I didn't, and normally how that works is you would heat up a solvent, say acetone, and allow the vapor to kind of consume the printed part, and it smooths it out. Well, I didn't have a way to, a good way to heat up the solvent, which ended up being nail polish remover, which is just acetone. And I didn't have a way to contain it. So I actually just brushed on the acetone using a paintbrush, which If you do this, go buy an acid brush. Don't use a paintbrush, because it killed my paintbrush. I ended up with some hairs in my finished part here. But this is what it ended up looking like. So I spent probably 20 minutes, maybe 25 minutes, painting on the acetone very liberally. A lot of it evaporates quite soon, but if you can build it up on the part, it tends to kind of micro melt it, gives it a little thin skin. So this isn't perfect, but this is actually a pretty good start if I was going to finish this any further. We have some pitting around where the surfaces were most shallow, right around the outlet there. Some pitting that would easily be filled with just some putty. So we could fill this and go ahead and sand it following if we wanted to. I didn't. I just installed as is because, again, this is sort of a prototype. And it's not the original design that I kind of envisioned. I envisioned something a lot thinner. So here's the bottom half installed. You can see I've hammered it into place. On the left and the right-hand sides, you can kind of see how this fits in. The firewall is only 50 thousandths inch thick. And so I made a slot in my part that was about 55 thousandths. I probably should have given myself a little bit more room. I made my part straight across, and it obviously fit, but I feel like this firewall had a little bit of a curve to it. And so that's where that's the reason why I had to hammer it in. But I didn't break anything. It seems to be working fine right now, but we'll see how it stands up to the vibration. Here's a shot a little bit farther back with both pieces installed, so you guys can see how that kind of cleaned up the area. That was the main goal. Up along the top there is where you're looking. And then here's a close-up shot of some of the issues. You can see in the top right corner, my tape template didn't account for the drop in height, so that doesn't match up. That's actually going to be a problem when I go to install. There's a seal that goes along the top there that seals against the hood of the car. That's going to be a problem. So I'm either going to have to cut that down or grind it down or redo the design. You can see how these fit together quite well. One of the issues is I think I'm going to have a hard time uninstalling this because I did have to hammer it down pretty good with a little ball peen hammer. So that's project number 2. Project number 3, wire T-box. All right, the problem, I had some exposed 0-gauge power wire under the dash of my car. This was a result of me moving the battery from the front of the car to the rear of the car. It's now sitting in the wheel well of the car. The solution, I was just going to print up a box to enclose it. I couldn't find a off-the-shelf product that met my needs. I couldn't find one to just purchase, so I printed one. Some added features, I added some debossed labels. So the battery positive, the lug positive, and to the fuse box, those labels in there are debossed into the printed part. It just helps somebody know if they're looking at it or if I forget how I wired the car, where these wires are going, because they're hidden. All right. This was printed on a Fortis 250 in ABS material at 10 thousandths of an inch slice height. Nothing, I know I wanted FDM because it's going to be, the durability is going to be needed, but it wasn't going to withstand high heat. It didn't need to have super high accuracy. So, just almost anything would have worked. The positives here is that it does enclose the T and it functions. The concerns, I totally created it the wrong size and it's a little bit too bulky. So one of the reasons why it's the wrong size, you guys can see there, I took my measurements from, I said data sheets, which means I looked up on the internet what size a 0-gauge wire was and also what size these lugs were. I just looked them up on McMaster-Carr because I designed this without actually going under the car and taking any measurements. That didn't work out so well. Probably shouldn't have done that, but hey, this design process is all about creating prototypes and learning from those prototypes, and I learned something here. So potential improvements, a better fitting part that might need a complete redesign because of how bulky this ended up being. In SolidWorks, how this kind of looked, the process that I went through. I've got my assembly here. Another thing that would have been an improvement is a lip and groove feature between the two parts. I should have done that in SolidWorks. They have a lip and groove command. I didn't do it. I should have. So if I reprint this, I'm definitely going to do a lip and groove. It just allows you to locate the parts a little bit easier instead of relying on the two fasteners. One of the neat things that you see a lot in 3D printed parts is when you're involving fasteners, instead of doing threads, we do a lot of through holes with nuts and bolts, and we use this sort of hex design to trap the nut. And that means we don't have to use any adhesive in this particular case. And it's a nice hidden way of using those nuts and keeping them out of the way. This part, a lot of it was designed top down, meaning in the context of an assembly. If I hide these parts, you guys can see my lugs in the center. All right, and I just built them around them. These were my best guess. There was some things that if I had gone under the car and taken measurements, I would have accounted for, like as I crimped these wires, they deformed a little bit, and as I put the heat shrink on it, they got a little bit, the diameter increased, so there were some issues with my part. There's the problem under the dash, exposed wires. Well, I have had this wrapped in electrical tape, but I needed something a little bit more permanent. These are locked together with a nylon lock nut, nice and secure, but kind of a danger. Here's the printed part. Nothing outrageously special about that. All right, so here's me increasing the diameter of the holes. Going back to the idea of you never get things right on the first time. Some things are totally your fault, and some things are not your fault. This is my fault. I just wasn't paying attention to the size of the holes that I put in here. So when I went to insert my screws, I think they were M6 screws. They couldn't fit. Luckily, I just popped them on the drill press, widened the holes, and made note as to what drill I used so I could come back into my SolidWorks file, update my CAD file to be more accurate. That's that iterative process I talked about in the beginning. You know, if we can go through one prototype, we're going to learn from it. If we can go through 3 or 4 different prototypes, we're going to learn more and more about our parts each time, and we end up with a more refined part. So here it is installed. It appears to fit very well because that's the angle that I took the photo from. But the two halves, the clamshells, they aren't really touching in all spots. And so it needed a little bit of a redesign, but it works. It's a little bit too bulky for me though. So I might come back and revisit this design because there's not a lot of space under that dash, but it's gonna work for now. So here's another custom part that something like this, customizable to say the wire sizes, would be an awesome product for a company to offer. All right, 3 down, 2 to go. It's gonna start to get a little bit more interesting. This is a throttle body spacer. The problem here is I have a water methanol injection system that I need to pump into the intake path. Water methanol is something that's used pretty commonly in motorsports. It pulls down intake temperatures and increases knock resistance in boosted cars. It allows you to run higher boost a little bit more safely. But the problem is you have to inject it somehow. In a lot of cases, they inject it in a couple different spots. One right after the intercooler. And the idea there is that the water methanol mixture would evaporate within the air, pull the temperature down as it does that. And it does that before it hits the throttle body, because you really don't want liquids touching the throttle body. But then you add a second injection port post throttle body between the throttle body and the cylinders. The idea there is that the water methanol would reach the cylinders and give it more, it acts sort of like an octane boost. It gives it more knock resistance and is actually a cleaning agent as well for your pistons and your valves and whatnot. So there's a lot of benefits to this. It's just got some logistical issues. This is another product that I could not find a vendor for. There was plenty of vendors for smaller size throttle bodies, like the OEM, the stock throttle body that was on my car. But I've upgraded the throttle body. It's from a 5.7 liter Hemi, which is funny seeing on a little 2 liter turbo car. Added features, none really. The injection port itself is kind of the feature. I measured this using a 2D scanner. So this is, I say 2D scanner, it's like your printer, scanner, fax machine all in one. I use this. I'll explain why. I printed it on the Fortis 400 that we have in Salt Lake City using the Ultem black material. The reason why I did it this way is because I wanted a material that I could install on the car and let it at least run and idle, get up to temperature. And that's exactly what I did with this part. Also, I needed chemical resistance if I do plan on keeping it for a little bit longer and actually inject the water methanol. I need a plastic that has chemical resistance, and Ultim is resistant, has methanol resistance there. So this was a good fit for a truly functional prototype. If I had done this out of ABS material, I would not have felt comfortable running the car with this installed. As of right now, I feel comfortable idling, letting it heat up, and I feel comfortable probably driving around a little bit. I'm not 100% certain how long I'm going to keep this in, but this is supposed to be a prototype, because I'm going to have to get one of these made eventually out of aluminum, or I could do some more processes to this as far as, say, infiltrate it with epoxy or sleeve it, and it could do a good job. Infiltrating the epoxy would be more for allowing it to hold pressure. That's one big concern here. So the positives, it performed at idle, which means it holds a vacuum pressure. The vacuum on my car is not high vacuum. It's about 6 to 10 inches of mercury. It's heat and methanol resistant. The concerns, maintaining a seal or maintaining integrity at positive pressure. So if I were to drive this around and go into a boost pressure, is it going to still maintain? I'm not 100% certain, but the epoxy infiltration would help with that. Another potential improvement here would be a deeper NPT port. So the port here on the nozzle, injection nozzle, is a 1/8 27 NPT port. If I made it deeper, I would probably have a better chance of the methanol not hitting the inside of the threaded hole, and maybe add an O-ring seal as well on the top there. So I created this from a 2D scan, and that's what you're looking at here. The 2D scan is actually of the gasket that I had to purchase to mate up between this part and the throttle body, and this part and the intake manifold. So the gasket's a perfect match. I popped this in my scanner. I put a ruler in there as well, and I just scanned this. I took the scan and I brought it into SolidWorks. So let's take a look at that part. The first sketch, if we edit this sketch, looks like this. Look at it on the top. This is that same scan. Starting in SolidWorks 2014, when you use a sketch picture, which is what this is, it's found under Tools, Sketch Tools, Sketch Picture. When you bring in a sketch picture, it brings in a scaling line. And so by including this ruler in the scan, I was able to zoom in really close, grab my scaling line, pop it between, say, 2 and 3, and then I tell SolidWorks that the line is now 1 inch, and it scales the image for you automatically. This is an awesome method. With this, I'm pretty confident that it's at least the image is scaled down to, it's accurate, probably down to a 64th of an inch, the image itself. And then from there, I use my sketch tools to just draw over the part. If I had more contrast in the part and I didn't have this background, the Cometic gasket background, I could have used auto trace as well within SolidWorks and probably got a pretty good job on that. Great thing about doing a 2D scan is that you don't battle perspective. So when you take a picture of a part, perspective totally skews your part. It makes your job so hard. So if something is flat enough that you can put it on a scanner and scan it, do that. It's going to work great for you. Here's the part as it's printed. This is black Ultem material. There's the injection nozzle and the tap. So I designed it with that through hole just set to a size Q drill, which is the tap size for a 1/8 27 MPT. I tapped that, no problem. Went through like butter. Here it is sitting on the throttle body. Pretty good match. Before I go on, I wanted to talk about one thing I did within Insight. So here is the model within Insight. And if you're not familiar with what Insight is the processing software for the Fortis level machines. So if you're going to be printing on a Fortis 250, 360, 400, 900, it's going to be processed within Insight. Insight gives us the ability to adjust the tool paths. One thing I was concerned about here was the part sealing against pressure, all right? Naturally, FDM parts are porous because of the physics of how the plastic is laid down. It ends up with internal voids. They're porous. But there's things that we can do to make parts less porous. The surface that I'm mostly concerned about is this interior surface because that's what's exposed to the intake. So what I did, let's go ahead and process these. I slice it up, slices it into the silhouette. Let's generate some toolpath on this. So now it's going to fill these silhouettes with toolpath, plastics. And we're going to be able to see the path the machine's going to take. All right, so I already had my custom settings set in before I did this. But what we see is what I did. If we look at this toolpath here, we have some areas that fully conform to the shape of the silhouette, and then we have some that kind of just fill in the rest. We call these contours and these internal portions rasters. Normally, you have one contour and the rest is raster. But what I did within the toolpath options is I actually set this to multiple contours, in this case 5. I increased the width of those contours to the highest as possible. And then I checked this box that says link contours. So what that did, those 3 steps together gave me a very thick skin that's continuous. It's continuous because of that link contours, meaning it's not going to do a circuit and then go straight over. It's going to bleed into the next circuit. So we found in our testing that this gives us the best sealing without any post-processing. This thicker skin. This worked great. It worked beautifully. I couldn't have done this if I had printed this on a U-Print or a Mojo or some of the more introductory level machines. It's kind of exclusive to Insight. So that's something that I took care of. Also, as I scroll up and we start to reach the through hole that's threaded, notice the skin is also thicker on the through hole, which I ended up threading. And by making it thicker there, it gave me more meat to thread into. So my thread's actually going to be stronger. So even if I didn't have to worry about pressure, if I was just going to do a threaded hole, this is something I'd want to do on a threaded hole as well. Because we don't want to be threading into the rasters, because that's where we get the voids, like you see up here in the top left corner. And here it is installed on the car here. So hopefully it's not too confusing the order I'm presenting this info. I see how it could be if you weren't 100% familiar with the setup of the car or exactly what the throttle body looks like or the intake manifold or whatnot. But what you're looking at here on the far left, you have a silicone connector that's coming up from the intercooler. The air is going to hit this throttle body. The throttle body is going to let selective amount of air in depending on the idle or the amount of gas pedal I'm applying. We have this spacer where it's going to be injecting some water methanol here, and it enters the engine at that point. So like I said, I did run this at idle, but I didn't go any farther than that. This is going to need further testing, and I'm not 100% certain how comfortable I am, how far I'm going to take it, but we'll see. The material itself, the Ultim material, it withstands the temperatures no problem. I was going to shoot this with my laser thermometer. Totally forgot, but just judging by the temperature of the coolant runs about 90 C, so 190 degrees Fahrenheit, give or take 5 or 10 degrees. This area here are going to be less than that, but even if the Ultim was in contact with 190 degrees Fahrenheit, would not be a problem. All right. Last but not least, the battery charging box. So the problem here, I relocated my battery from the engine bay to the rear of the car. I did it mostly for visual, and I didn't want that battery in my car or in the engine bay, but it caused a lot of headache because another thing that I've done to the car is they call it shaving. I shave the back hatch of the car. So I have actually removed the handle and the lock on the back of the trunk, which means I can't physically open it with the key. I have to hit it with my key fob. It's all electronically controlled. Well, as it goes, sometimes batteries die. Or when you're tinkering on your car, sometimes you fry a fuse or it drains out. The problem was I couldn't get into the car at that point through the back. I had to climb through the car and open the hatch manually from inside, and you can only do that by removing the inside plastic panel. So it was a huge headache, but I dealt with it because I'm a car guy. I dealt with it, but I wanted a way to be able to jump the car without destroying the inside, climbing through the inside and removing the interior panels. So I wanted some charging posts in the front. Added features. I added a voltmeter in there because why not? This is one of the things that I talked about, feature creep. Do I really need a voltmeter there? No, but I had some extra space there and I wanted to do something kind of cool, and 3D printing allowed me to do that. This is actually going to help me read out what my current voltage is and also let me know how far along, if I'm charging the battery, how far along it is, or even if it's working. Measurements were done using photos and paper templates, so I have some pictures of that, and we'll talk about some of the difficulties there. This was printed on Uprint SE Plus, so Uprint SE Plus is limited in size to 8 by 6 by 8, and that changed my design. I originally designed it for the Fortis 400, but availability of the machine, I needed to put some other parts on there, so I had to make this a little bit smaller. That created some issues. At 13 thousandths of an inch, which is coarse, but I didn't see the same issues that I saw on that wire feed-through part at this coarseness because of the geometry. I'll show you a picture of how I created this, but we have a lot of flat surfaces, a lot of vertical surfaces where we can get away with a more coarse print. Positives, functions perfectly. I can charge my car now. The voltage reads out great. Concerns. This required some manual rework. I had to take my Dremel to a couple portions of this because I took some guesses instead of measuring in some cases, and I guessed wrong. So I had to adjust some of the parts with my Dremel. And actually, I made a mistake as well, too, in the design of it. So I'll talk about that. Potential improvements. I would actually like to have this larger overall size, larger internal space, larger wire openings so that the wires aren't held as tightly as they are, because there's going to be some issues there with the engine moving and this not moving. And also, I want to kind of do a hydrographic finish on that. So this is how this started out. I laid down some painter's tape, kind of the outline of what I wanted. And then I took a picture of this with the ruler in there for the same reason I included the ruler in my 2D scan. I used a marker to indent some of the bolt holes there and kind of mark on the tape where I wanted my part to end. And one of the things here is this is a photo. I did my best to hold the camera straight above the part and as far away as I could, but I still had issues with perspective skewing the photo here. So it's very hard to take accurate measurements with a photo. The best thing that you can do is stand as far away as possible and use a zoom lens. If you use a zoom lens, you're going to have less issues with perspective. The image is going to appear flatter. But if you have to stand close and you can only use a focal length of, say, 20 to 50, even up to 70 millimeters, you're going to have an issue with perspective. And I had that here, and that's the reason why I kind of did a two-step process. So I fed this image into SolidWorks. I created a very basic 2D shape, and then I took that 2D shape into a SolidWorks drawing, scaled 1:1, printed it out on my printer, and then cut it out, and I end up with this. So now you're looking at a version 2 of the template. This is printed out on paper, and you can see I was pretty close, but some of my bolt holes didn't quite line up. And so I took this image, fed it into SolidWorks, and adjusted the location of my bolt holes, and I ended up with something that ended up fitting. So this was a two-step process. If I had a handheld laser scanner, that would have been great, at least for the bolt hole locations. But this ended up working. It took me, maybe an hour to do all of those steps. Something I'm doing more and more is printing out 1:1 templates for things. So I modeled this up. I printed it in the Uprint. This is how I printed it, the orientation. What I was looking for here is, one, I wanted to fit it all in one build tray so I could run it overnight. But two, I wanted vertical surfaces, because vertical surfaces give you the best surface finish. All of this support material I removed by hand. One of the big things we talk about is soluble support material. I could have very easily just put these in the water tank and let it dissolve, but I was in a hurry. I wanted them done quick. I removed all of this by hand and I used some pliers, and it took about 20 minutes to remove all the support material. All right, here's the part. Here's the lid as it's finished. Notice one of the things on the left-hand side, the recess for the voltmeter. I added some corner relief in there because I wanted a nice tight fit. But, you know, the corners become an issue at that point, so I added some corner relief. That's one kind of added feature that you wouldn't normally do unless you were 3D printing it. There's an issue with this image. I don't know if it jumps out to anybody. It didn't, certainly to me, until I actually tried to put the battery posts into those holes. But those holes are not the same size. So I don't know how this happened. I'm the first to admit mistakes normally, but this was not my mistake because I went back into my SolidWorks file, I checked my sketch, I had used a symmetry sketch relation on the holes, I had mirrored it, they came out different sizes. The sketch was fully defined, I have no idea how this happened, but I dealt with it. So this is something that if this mistake had been found out later, if this was a real product and I had sent this out for manufacture, this would have been a huge cost and a huge delay in production. I was able to find it in the physical prototype, and it actually didn't take looking at it. It actually took me trying to assemble it until I found that. So this is what I did. I printed out another, I changed the model, printed out another one, scaled 1:1 drawing. I taped it onto the part. I marked it with a marker, and then I used my Dremel to just grind it to size. So it wasn't perfect, but it got me to where I needed to be in this prototype. This is my little setup for the voltmeter and some of the wiring I had to do. One of the unique things about this setup is this 0 gauge wire is pretty thick. It's about 5/8 of an inch thick. But this wire that I've been using, this power wire, the black wire that you see, is from a company called Nuke Concepts. And it's pretty awesome. This particular one is stranded, copper-clad aluminum. I could tie that wire in a knot. It's very malleable. So this is what the backside looked like. Here's another potential design improvement. The battery lugs, you can see 2 of them there. They have a retainer kind of like on a electrical enclosure box. I have those retainers installed upside down though because they didn't fit the other way around. They have some sharp points that are supposed to dig into the material, but I didn't have enough threads. So a design improvement would be adding a recess into the back of those panels so I could install those correctly. The way it is right now, I'd be concerned about those loosening. I also went through the trouble of extending those wires, and then I realized that I didn't have to because they're going to reach just fine. One thing I did have to do, another adjustment here, just to go to this next image real quick, I had to grind off the side of the voltmeter. This is something that I ordered off Amazon Prime, overnight shipped it. I didn't have it on Friday when I designed this part, but I wanted to install it. It was one of those feature creep issues. So Amazon Prime's great, you know, $4 overnight shipping. I found in the comments on the listing the size of the part, and that's what I designed my part around, but it wasn't quite accurate. So I'd ground off one portion there. This was a pretty necessary step of the process, crimping these wires. This is just a case of having the right tools for the job. This would have been a very difficult job to do if I didn't have the ability to crimp these lugs here. All right, and this is the installed. So you can see I skipped a few parts as far as post-processing the printed parts. I did kind of a 2-step post-process. You see down in the bottom corner there. The printed parts have been sanded. I sanded them with 150 grit sandpaper, and then I painted them just using regular Rust-Oleum spray paint. I used a sandable primer, and then just a gloss black enamel. The voltmeter's all set up. We've got power running from the main ground wire is actually internal on the frame in there, and then the positive wires coming from the starter there, just on the left. A little bit closer view, I've got some socket head button cap screws. Voltmeter's reading 11.7 volts, so it's a little bit low. Car's been sitting for a while. One of the challenges here was the size of the wires within the container. we can see the 2 ground wires that were existing down in the bottom left. Those are ground wires for the radiator fans. That's an area where I had to enlarge in it with the Dremel because the opening that I made wasn't quite large enough. And here was the whole shebang of it. This is the reason I created it. I wanted to be able to charge my battery more easily. We can see I've got the chargers on there. The voltage is now reading 12.7. Everything's functioning correctly. So I was pretty happy with that. As I was designing it, I was thinking it would be pretty cool to have it look like carbon fiber. I knew I wasn't going to make it out of carbon fiber because I had all sorts of mounting bosses, all sorts of weird features going on in here. But one of the cool things that I've been made aware of is the idea of hydrographics. So I asked one of our guys at Go to use bunk speed to give me a render so I could see maybe what it would look like if it was carbon fiber. I thought that was pretty cool. So I think what I'm going to do is I'm going to spend a little bit more time on the finishing and then have it hydro dipped. Hydro dipped is pretty cool. You would take a part that's finished, it's painted, in this case, say gloss black, very nice finish, and then you dip it onto a film that lays on water, and that film has a pattern on it, in this case, like a carbon fiber pattern, and it conforms to, the film clings to the part, conforms to shape, and then you pull it out, you dry it, and then you clear coat it, and you end up with a part like this that looks like carbon fiber, but is not really carbon fiber. This is huge in automotive and the gun markets, so I might end up doing that, make it look a little bit better. All right, so that's about it. I didn't even come close to sticking to my 30 minutes. I'm sorry about that. Lessons learned: no parts designed perfectly the first time. Sometimes that's you as the designer's fault, but also it can be the faults of the software, it can be the fault of the vendor, their requirements changing, their needs changing. Just it's accepted throughout the world that no parts designed perfectly the first time. But failed experiments, failed designs are part of the design process, and we can learn from those. So there was definitely some things within those parts that improvements that I want to make. I wouldn't have known those improvements until I had a physical part in my hands to assemble and made up to the car. Another lesson learned: Dremels can and will fix your mistakes sometimes. So I made a good use of my Dremel tool, but I also made good use of learning from those mistakes, going back to my CAD design, and making adjustments to my models so that they were more accurate and they were better designs. That's the iterative process. And then also I learned that 3D printing is pretty versatile and enables smarter designs. It's versatile in the fact that I can print parts that go in the interior that look good, that are very smooth finish, very small features such as threads, or I can make parts that are durable enough to be mounted to an engine and run, and are going to withstand heat and chemicals. So 3D printing is something that people are becoming more apt to experiment with, but we got a lot more experimentation ahead of us. So that about does it for this webinar, 3D printed car parts. I hope this was kind of eye-opening to some people. I had a lot of fun doing this webinar because it was more personalized and I could speak more to the parts themselves. I think I might start doing these for our monthly webinars, something a little bit more personalized. Again, this is being recorded, so go ahead and log into our YouTube page if you want to revisit this. If you're watching it on YouTube later on, thank you for watching. Check out some of our videos and have a great day.